Hi everybody and welcome to another video. Today we are going to talk again about Comet, Atlas, and especially this particular picture. Now this picture is something that was floating around now since around a week on different social media networks and also in the media, and some people claim that this cylindric shape is very weird of the comet and it cannot be natural. It indicates some kind of artificial origin. Now the picture you see again here has been recorded from the NavGam camera on the Perseverance rover on Mars. And although the texts are very large, claiming that this is something very strange and there's no real actual explanation how this particular cylindrical shape can happen, we will use Python and only a very short script, or not short, but a few lines of code to debunk this claim and show that everything is, let's say, normal. So, without further ado, let's dive in. Now, the very first thing before we dive into our coding is using Stellarium, the open source planetarium software, to get a little bit an idea of what we are going to do. Because the cylindrical shape of Comet Atlas is not due to its artificial origin of being a cylindrical object. No, it's a very simple optical effect by when you record something in the night sky with any camera. Now here we are on planet Earth with the night sky. This is now end of May this year. Just set it up a little bit, and we are searching for a for an asteroid called Vesta. So Vesta here is a pretty large object. It's a bigger asteroid in the solar system, and here we are. Now the thing is though that the cameras of, for example, Perseverance or other cameras of the rovers, they are locked to the star, to the starry night, to the stars and the movement of the stars, the apparent movement of the stars, because they are also being used as a navigation camera and they use the stars to orient themselves. It doesn't matter whether it's an orbiter or the rovers, they use the stars as fixed points. Now, instead of looking to Vesta, let's take this star here, this Sigma 1852. I don't know, never heard about it. And we are locking our settings to the star. Now, we also use the equatorial mount, which means that we are aligning with the sky's north pole, let's say. And what we do now is we take the date window part, the small window here, and we are increasing now the hours. And take a look at Vesta, what will happen. Yeah, we are moving a little bit to the night sky. The stars are fixed, and you see that Vesta is moving. Yeah, because Vesta has an orbit around the sun, and its apparent movement in the night sky with respect to all the stars is kind of significant. Of course, the stars are also moving, but very, very slowly. Some are moving by a few arc seconds a year, or not even arc seconds, milli arc seconds. But Vesta, on the other hand, moves with high velocity compared to the stars. And there is no difference with Atlas, actually, because Atlas is closing by with Mars. And it's also a minor object, it's a comet, and the same geometrical thoughts, implications apply also to planet Mars. So instead of a fixed star or fixed light point, we have something that is moving across the camera while we make several images. So how can we do this with Python? I would say let's switch to my GitHub repository first. And on my GitHub repository, we have another script here in the compressed cosmos folder. It's getting kind of crowded, I admit, so maybe in the future I should consider to reorganize everything, but as long as there are no complaints, I'm fine with that. And you can simply click on Open in Colab, and then it will open in Colab and we can start working on it. But instead, I would say let's go line by line or cell by cell and think what this really going on. Now let's take the very first cell, just copy pasting it. We need to install Skyfield. There's an application for Python for handling orbital elements and something like that. It's not as complicated as Spice, if you may have heard about it. It's way easier to use. And we need something called a Spice kernel. Maybe you've seen it from my previous videos, that contains the apparent movements of the planets. In our case, we use the kernel de432s.bsp. And here we have the index. And why did I choose this one? There are a lot of different kernels. We go to the summary file. And if we check for the, what was the number again? 432s, we cover a date range from the 1950s to 2050, so 100 years, especially our time range now, 2025. And this file is also particularly small. It is only 10 megabytes of size, so we don't need to download a gigabyte or 100 megabytes. I know these are very small files, but we don't need to download them all in our Colab network, Colab environment. So let's do this here. We install the application and we download this file as well. Now, the very first thing is that after installing and downloading everything, I would like to download cometary data. And there's like a big ground truth for cometary data, and it's from the Minor Planet Center. And for this, we need okay, some German word popping up. Skyfield. There's already interesting this auto completion with Gemini, but well, Gemini doesn't really know what I want to do, so let's do it manually. We need the Skyfield API and the data. Just forgot the data. MPC is the Minor Planet Center and Skyfield.api. Yeah, I just look, of course, sometimes to my master solution, so don't be confused with that. And now we need to read in the data, so we do load.open. He suggests me to load the kernel file, but this is not true. We want to get the Comet URL. So there's like a fixed, a hard-coded URL where we have the cometary data, the Comet data from the Minor Planet Center. And we simply download it. So currently we have, I think, something like 1,000 or so. So we simply call it comets.df. And then we have mpc.load and then Comet's data frame. This is what we need. And then f. And then we can also maybe show that, print the size of the data frame. So this should be quite quick. And then we have around 1,220 comets. So if we just take a look at, for example, the very first 5 lines, we see here the perihelion month. We have here the perihelion distance, the eccentricity, the argument of perihelion in degrees, and all the other orbital elements, also the magnitude values, and then also the designation number. And the designation number is the number we need to find the Comet Atlas. Of course, I played around before. I know there's only one that has this correct designation, and I want to get rid of that. This is really annoying because this is also not correct, because Atlas is a substring and not really the designation of it. So I know that there is like the name Atlas inside. So we designation. So what we do, we take the pandas data frame, we take the column designation, we handle it as a string and check if it contains the word Atlas or 3i. Really doesn't matter. I think maybe there are other Atlas comets already, so check it out for yourself. And then we simply copy it. So the Atlas DF, let's check how it looks like. This is now a single line, and it's here the designation 3i Atlas. Now we can check also the most recent eccentricity values. This would be interesting. 6.138. That's very eccentric. That's very hyperbolic indeed. And now what we want to do is, I want to, let's say, simulate a little bit a camera, right? So I observe the comet at a particular time, check for the position and right ascension and declination, so the sky coordinates, and then I recompute the coordinates 5 minutes later, let's say. Yeah, it's not a very unrealistic, because the cameras make several images over a longer time window. And then we compute the angular distance between these two these two values. I have to copy one thing. We need namely the gravitational parameter of the sun. And then we have to also convert our Atlas data frame to a row, because yeah, the part we will use in Skyfield cannot handle the data frame itself. Doesn't matter really. What we need now is we need to use the time scale. So we, as you may know from SPICE, for example, there are like the time kernels and so on, but here Skyfield is doing everything for you. Then we need the ephemeris. For this, we need the load function, and then the ephemeris part we just downloaded. Hey, come on. S. No, it's DE4, right? 432S. This time there's no auto completion. Let me check if this works. Okay, that's strange. It wants to download it, but I already downloaded it. Okay, it didn't find it locally, so it tried to download it by itself with a wget command, but we already downloaded it, so it really doesn't matter here now. And then we compute the positions for Sun and Mars. And for this, we use the ephemeris position of the Sun and then the ephemeris position of Mars. Now something will happen. There will an error spawning, because in our kernel we have, for example, the position of the Moon and the Earth. You see it here below, or Venus, but not for Mars. For Mars we only have the, where is it? The barycenter. So the mass, the center point when you consider Deimos and or let's say it's two moons and Mars, the mass of these two moons is very, very small. So the barycenter is almost where the geometric center is. But since we don't have the wording, we need to use the word barycenter here. So we have Earth, Sun, and Mars. Now to compute the position, we can say, okay, we take the position of the Sun plus the mpc.comet orbit. And for this, we take the Atlas row, the timestamp, and also the gravitational parameter of the Sun. So this is like where we will compute, let's say, the vector or the position of the comet. So this is what we have. And now we can compute the position as seen from Mars for two different time frames. So we say we have something like T1 is equal to, let's say, the time scale UTC, and then we have year, month, day, hour, minute, second. And I just used my master solution, where I simply choose the 5th of October, and then we can copy paste it here, let's say with T2, and then let's say 5 minutes later or something like that. And then we can compute the position. The first position is then the position as seen from Mars. So we take Mars as an input. So we already see here the auto-completion. Mars at a particular time spot or timestamp T1, and we want to observe something, namely the comet. So this is for the first time, and this is for the second time. So we will compute the positions for these two particular time stamps, and then we can compute the angular distance between both positions. And this is also pretty nice here, solved in Skyfield, because this is wrong. We need to say comet.pos1.separation from comet position 2. Let's see if it works. Separation, right? Yes, separation. That's good. And we have here a result of around 2 arc minutes and 16 arc seconds. So what does it mean? Of course, our comet is not a very sharp dot on a single pixel. Yeah, it's smeared over several pixels, of course. But the resolution of 1 pixel for the Perseverance NavCam camera, I think in one of its settings, it was, I don't know, if I recall correctly, it was like 50 arc seconds or something like that. So 50 arc seconds is almost an arc minute. So after 5 minutes, the comet moved already by 2 pixels. And of course, the camera didn't record it for 5 minutes because it's a very big scientific discovery. It was recording it over several minutes, several hours even, and then stacking the images. And since we were tracking the stars, the comet appeared as a small line. So the thing is that the small line we have seen in the beginning of the video is not some artifact or not the reason of being an artificial object. Again, Occam's razor, instead of claiming it is some artificial probes sent by somebody here, intentionally or unintentionally, the model with less parameters is simply that we have a camera that is locked to the stars and the comet is just trailing on our camera sensor. So I'm sorry to destroy any hopes of the comet being a very cylindric object. Maybe it is even, I don't know. Yeah, maybe we have to check it out and see the shape of the object. But considering our knowledge of comets and considering also this particular effect, the claims that you read online, whether it's on Reddit or other media, is most likely not correct. Thanks for watching.